Hi students, in this video we are going to see one of the crystal defects, that is non-stoichiometric defect. So let's understand what is non-stoichiometric defect. Non-stoichiometric defect is a defect that causes a ratio difference in the number of anions and cations. The ratio is affected here. A difference in the ratio of number of cations to the number of anions is caused here. So example, if two substances like NaCl has 1:1 ratio when they are reacting, and the formula is 1 sodium combines with 1 chlorine, 1:1 is the ratio. Now in a non-stoichiometric defect, this ratio gets affected because the number of atoms may not be equal. So it will cause some defect. That is called a non-stoichiometric defect. Now there are two kinds of non-stoichiometric defect. One is a metal excess defect, and the other one is a metal deficiency defect. So let us understand the metal excess defect first, and metal deficiency defect after that. Now what is a metal excess defect? It arises due to anionic vacancies, due to the presence of excess cation in the interstitial site. Now you can find here in this crystal, here we have the anions and the cations. And here see, one of this place is vacant, only an electron is there. So anion, this cation A plus and anion B minus, it is arranged properly, but at this place we required a B minus. An anion is required, which is missing, only electron is sitting there. So it causes an anionic vacancy. Anionic vacancy. So this is a metal excess defect. Here the metal ion, cation is in excess compared to the number of anions. Now in this crystal you can check, the anions and cations are arranged properly. A plus, B minus, they are very systematically arranged. But you find in the interstitial space, in between, there is an A plus, that is a cation is here present here. So the cation that is there in excess is also causing a defect here. So it is an excess of cation. Now the next thing we can see is, when you talk about sodium chloride crystal, because it is a very systematic and ideal crystal, the kind of defect that we see in sodium chloride, when crystals of sodium chloride are heated in an atmosphere of sodium vapor, the sodium atoms get deposited on the surface of the sodium chloride crystal. What are we doing here? Sodium chloride crystal is there, which has got systematic arrangement of sodium and chloride ions. Now we are heating this crystal in an atmosphere of sodium vapors. Sodium vapors are surrounded everywhere. Sodium vapors is there around the metal. So on the surface, the sodium metal atoms come in contact. See, the crystal has Na plus ions and Cl minus ion. What comes around on the surface is Na atoms. It is not ion, it is Na atom. Now what happens is, the Cl minus inside, the Cl minus present inside will come to the surface. It will move to the surface, and what they will do, so come to the diffuse to the surface and combine with the sodium atom. So what is coming here, you can see here, Na is there. Na will lose one electron and form Na plus ion. The Cl minus comes from inside, combines with Na plus and gives NaCl. Now what is left is, this electron is left with no place to go. Now NaCl is formed here. The Cl minus from inside has come to the surface, but it leaves a vacancy from where it has come. So what happens is, the electron goes inside. The electron left here will go and occupy the place from where the chloride ion has come out. Now we get a defect in the crystal. So the vacancies, the diffused chloride ions will combine and come to the surface, and the electrons will diffuse into the crystal and occupy the vacant site. So this is a kind of non-stoichiometric defect that is caused in sodium chloride. Now what will happen in the crystal because of this? The crystal now has an excess of Na plus ion, because the chloride ion has moved to the surface. The crystal now has the Na plus ion in excess there. So anionic center, there is a vacancy created where the electron is sitting. It's called an anionic center, and where there is no atom, no ion, only electron is sitting there. Such centers, such vacant centers caused by the diffusion of chloride ions to the surface, and only the electrons are moved in there, only electron present. Such centers are called F centers. F centers. Now F stands for Farben center, which is a German word which means color center. Now the color is created. How the color is created? When sunlight or any bright light falls on the crystal, what happens is the electrons, this is an unpaired electron, a single electron, so we can call it unpaired electron. The unpaired electron, as you know, it absorbs energy and it will get excited. It excited to a higher orbit level, or it moves from its original state, and when it moves up and gives out its energy and then comes back, this is what is called excitation. The excess energy absorbed, it absorbs energy from the visible light falling and undergo excitation. Then it gives out radiation. The radiation will give certain color depending on the frequency of the radiation. So here we have a color created. So since it imparts color, it is called F center. Now example, if you see sodium chloride, when Na is put on sodium chloride, excess of Na in NaCl imparts yellow color. So this is something to note. Yellow color comes when sodium is put in excess on sodium chloride, and when lithium is put on lithium chloride, it imparts pink color. Same way, when excess of potassium is put on KCl, it imparts a violet color. So this way, color centers, it absorbs, it gives out color because it absorbs energy and undergoes excitation. Who is undergoing excitation? It is the electrons in the vacant centers which undergo excitation. So it is called F center. Now if you take another substance called zinc oxide. Zinc oxide is also known to change color. When zinc oxide is heated, it turns yellow. So zinc oxide, everyone knows about that, you must have studied already. So zinc oxide is yellow when hot. Yellow when hot. And it is white when cold. So this is something interesting. When the temperature changes, the color changes. See this. So what is happening in zinc oxide? So here there is a metal defect that is causing the excitation and the color. See, if zinc oxide turns yellow, when heated acid loses oxygen, this is ZnO, and it changes to Zn++, and half O2 or one oxygen atom is given out, and 2 electrons are also given out. Now in the crystal, since the oxygen is lost, there is an excess Zn++ ion because the oxygen is lost. Now oxygen is a gas, as you know, it escapes, but zinc being a solid, it stays there, the zinc ions. Since it has left its place and unable to stay there, so what happens is the Zn++ has to occupy an interstitial space. It stays in the interstitial here, which is in the mobile condition, and the electron, excess electron produced, will also be there in the interstitial space. So there will be some free moving electron here and Zn++ ions here. Now these will undergo excitation and that will give the color. So that is why it turns yellow when heated and white when cold. The formula now changes from ZnO to Zn1 plus XO. Zn1 plus XO. So because there is zinc, excess of zinc is there, 1 plus X, number of zinc ions created on this, that is X into O. So there is an excess of metal ion here. So it's a metal excess deficiency. The excess zinc atom moves to the interstitial side. Electron moves to the neighboring interstitial side. So it gives excited color. Now the other kind of stoichiometric defect is the metal deficiency defect. Metal deficiency defect, as you know, it shows there is a deficiency of metal. It is very common in materials like this FeO crystal. FeO is Fe is here in +2 state and O is in -2 state. Ferrous oxide we can say, or iron 2 oxide, whatever can call it. So what happens is cations go missing here in this from the lattice sides. Look at the crystal here. Fe plus 2 plus and O 2 minus. So they are very perfectly arranged here. Now sometimes what happens when Fe plus ions go missing here, how it is happening? It is being replaced by Fe3 plus ions. Some oxidation is happening. Fe2 plus gets replaced by Fe3 plus ions. Let's see how it happens. So the electrical neutrality is maintained. How it is maintained? So you can see the electrical neutrality because Fe2 plus ions are coming and see they are leaving and Fe3 plus ions are coming. Now the numbers are maintained. How? 3 Fe2 plus, 3 Fe plus ions are removed. They go out. What comes in is 2 Fe3 plus. So 2 atoms, 3 atoms. Total charge 3 into plus 2 is plus 6. Here also 2 into plus 3 is plus 6. So neutrality is maintained. The charge is equal, it is balanced. At the same time, number of atoms is decreasing. 3 Fe atoms leave and 2 Fe atoms come. So there is one vacancy created. One Fe atom is not there, it is missing. So there is a metal deficiency caused. The crystal has this defect. Now if you take a FeO, we know FeO is 1:1 ratio. 1:1 ratio means in 1 mole of substance, if you take 1 mole of FeO, how many Fe atoms are there? 6.023 into 10 to the power 23 atoms of Fe are there, same or ions. Now same number of oxygen is also there. Oxygen also 6.23 into 10 to the power 23 ions, oxide ions, same here also ions. So we have equal numbers. Now what happens in a crystal, 1 molar substance, a few Fe2 plus ions are missing, instead Fe3 plus ions have come. So total number of Fe, if you count, it will be less than this number. So the ratio 1:1 will not be maintained. Oxygen is the same number, whereas Fe, the number of Fe atoms decrease. So usually FeO has a formula of Fe 0.95:1. So instead of 1:1, 1:1 changes to 0.95:1. So because Fe atoms are decreasing in number. Generally it varies from 0.93 to 0.96. The average usually found is 0.95. So this is a metal deficiency defect. Now other examples are iron sulfide, FeS, and nickel oxide and titanium oxide. All these substance compounds also show this kind of defect. So that is about a metal deficiency defect. I hope you understood this. Now students, you can comment on this video, whatever you have seen, if you understood, or you can subscribe and you can watch the video again if you want to understand better, and you can write your comments. Thank you.